This is a lecture video on how to calculate an excavation volume. Corresponds with math sheet or problem number 2 for F-line on excavation volumes. Now it's a combination. These sheets are a combination of establishing the excavation elevation at the bottom of the dig. So we'll go through that process first, and then we'll get into the calculation of the volume itself. First thing I want to alert you to on this sheet is that the drawing is misleading. The drawing has a downward slope, implying that where the dirt hits the building is lower than the benchmark elevation. It's not true. It's a plus 2% grade. So it's correct to view this slope as moving upward. And hitting the wall just a bit higher than the elevation of the benchmark. Okay, then you have a 235 millimeter protrusion of the concrete above the dirt. So we're going to get our elevation at the top of the wall with those calculations, and then we're going to subtract the wall height, which is here. These are all in meters or millimeters, and we're going to subtract the footing thickness. So we'll start with that. This will be the second half. We'll cut to that after. So our first move is to establish the elevation at the bottom here. We do that by using our ratio and proportion calculation based on our setback, which is 9.144 meters from the benchmark to the building. I also have the triangles drawn upside down. It's actually going to be an increase in elevation. Just take note of that. And this is our 2% slope, written out in a ratio form. A previous video will explain that a lot better. That's basically the first portion of F-line math that you go through. So this is almost like a review of that. So first thing we're going to do is establish that height difference based on this ratio. Okay, and I like to write these out in fraction form. So we have this x value, the short side of the triangle, fractioned out with the setback. And you can see the proportional triangles. The 2 would be opposite the x, and 100 as in 100% will be opposite the setback. So to find x, we're just going to cross multiply and divide, and we find out that x is 183 millimeters higher than our benchmark. So that's the first step. Now let's figure out the elevation at the top of the wall. We'll take our benchmark. We're going to add x, which we just found. We're going to add that 235 mil, which would be left over exposed part of the wall, and we get an elevation of 100.418. Okay, and then our next step from that is to take that elevation and subtract these two out to get our elevation at the bottom of the hole, and it comes out to 97.78. A couple other things having to do with elevation here. The sheet is asking you to figure out it's important to understand the average elevation at the top of the excavation. Okay, we need that to figure out our depth of cut. So we're going to take these 9 values. This corresponds again with D line. Right, you would have set up your instrument, shot back to the benchmark, figured out your height of instrument, and then you would have taken rod readings at these 9 locations. And then you would subtract the rod reading from your height of instrument to get the elevation at each spot. Okay, so we're going to take these 9 values, going to add them all together and multiply by 9. That's what I've done here. Okay, I didn't show it, but that's what it is. So that's the number that comes out after you've found the average of those 9 spots. So the average elevation at the top is 100.50. Okay, now we can get our depth of cut. We take our average elevation at the top, subtract our elevation at the bottom of the hole, and the difference between the two is going to be your average depth of cut. That's what we've got here. So our average depth of cut in this case will be 2.72 meters. And a few other things that they're asking you to do up top there is just to establish the depth of cut at each of the 4 corners. That's just a simple subtraction, taking your elevation at each corresponding corner and subtracting out the elevation at the bottom of the hole. It will tell you how much dirt you need to remove from each location. Let's get to the excavation volumes now. Okay, so the first thing I like to do when I'm doing this math is to write out the formula itself, get a good visual on what you need, and then you can figure out what you don't have and find that. So we have the area at the bottom, and this is straight out of the textbook, F-line. Area at the top, plus the area at the top, sorry. Divide that by 2 and multiply by the depth. We just found out the depth of cut, so we have that. We don't have these two. So let's start with the area at the bottom. So I have the building size, and then I have a working clearance, or a working allowance, whatever you want to call it. Okay, so that is going to constitute the area at the bottom of our excavation. So we're going to need to dig out enough of an area to capture the building, plus a working clearance all the way around. So this solid line indicates the building, and these are the building dimensions. And this dashed line indicates a working clearance allowance that we have, which we're calling for here is 0.6 meters or 600 millimeters. So what you need to do is figure out the total area at the bottom of the hole. Take the building size, and we're going to add that working clearance. That's 0.6 meters on each side. That's what I've done here. So these numbers now will get increased to 19.6 in this direction. And here we have the 23.6 plus working clearance in both directions gives us now 24.8 meters. So the area at the bottom of the hole, length times width, are those two new values that we got. And it gives me this number. This should be squared, meters squared, 486.08 meters squared. Okay, so that now we have the value to plug into our formula here. We just need to determine the value to plug into our formula at the area at the top. So let's go through that next. So area at the top, I've drawn out a rectangle again. I'd like you to notice that the rectangle I'm using now, so if you visualize yourself looking down from the sky, this is the area at the top of the hole. So this solid rectangular line here constitutes the bottom of the hole, which we just calculated. Remember, the bottom of the hole was the building plus the working clearance all the way around. This is a mistake, 23.6. It should be 24.8. Okay, I just didn't add the working clearances. Okay, so I want you to look at this here and see that it's 24.8, which we got right here. Okay, so what we need to do, because we have a sloped excavation, so the sides of the excavation are sloped for safety, we have a ratio that's required for us to establish that slope. That's the slope ratio, or the angle of repose, we also call that. We use this graphic here to signify that for every 3 on the horizontal, we need to be 4 on the vertical. That's just a ratio, remember, those aren't numbers, those aren't meters, don't get confused. Okay, we need to turn those into meters. So again, our ratio and proportioning comes into play. I'll just read this out for you. The area at the top is bigger than the bottom by the horizontal component of the depth of cut as we proportion it off against our angle of repose. Okay, I hope this makes sense. So if you can see here, we can actually proportion these two off just like they would be a triangle. We need to figure out the actual horizontal amount that the top of the hole is going to be wider than the bottom of the hole. So we'll take these two values, we'll stick them into fraction form yet again. We're trying to solve for x, so we take our 3 and multiply by 2.72, divide by 4. That tells us that the amount of distance, the top of the hole is going to be wider all the way around by 2.04 meters. Okay, let's go back to our graphic. I've indicated that here. Okay, so as you're looking down, you're looking at the bottom of the hole and the top of the hole. And there's a bit of a slope there. So we're going to increase the area at the top by that rectangle, those rectangle dimensions at the bottom. Again, this is 24.8, not 23.6. And then we're going to increase that by 2.04 all the way around. Okay, and I've done that here. And the new triangle, or new rectangle, sorry, for the top is 23.68. And the new rectangle dimension for the length is 24.8 plus the 2 horizontal dimensions of our angle. Gives me 28.88. And I've squeezed in the area for the top up here, length times width, with using these two new numbers. It gives me 683.878 meters squared. Let's go back to our formula now, just to wrap this up. I've got everything I need now to punch into my volume calculation. I've got my bottom of area at the bottom of the excavation, area at the top of the excavation. Divide that by 2, multiply by the depth of cut, which was 2.72. Gives me 1591.14 meters cubed, or cubic now. Okay, that's a volume. And our last step is to add a bulking factor. And it was mentioned, I believe, on that first page that the bulking factor will be 20% for this situation. This has to do with the porosity of the soil. Okay, so in this case, we're going to add 20% to the volume of the excavated material. To do that, you can just multiply this number by 1.2, and you get a total of 1909.37 meters cubed. So that tells you how much dirt roughly you're going to be removing from this excavation. And that's the gist of this math. There is one last thing that we ask you to do on these sheets. Calculate the rod reading at the bottom of the footing. I'll talk about that briefly. All we need to do for that is take our height of instrument, which was given to us, and our elevation at the bottom of the hole, which we established with our math. And it tells us that the rod reading from the instrument set up at this height should be 3.45 meters at the bottom of the hole. So if you can visualize yourself with an excavator machine digging out the hole and taking continuous readings with your instrument until you get down to 3.45 meters on the rod, then you know you're down at the right excavation elevation. Okay, so I'm hoping this video helps clear up a lot of the gray areas with these sheets. I know the answer keys aren't as clear as they could be. Okay.